Hello. I haven't done this in a while, so okay, let me share like the Firefox just in case. So, oh, how does this look? Okay, so just to let me minimize myself. Uh, yeah, so if you go to the Canvas side, that is where you can find the information about the course. I have like, let me see if I can zoom in a little bit. I have some office hours, which, they're kind of like preliminary office hours. Obviously, like, once we're closer to a particular exam day, I'll have more office hours and like, uh, the TA will have different office hours. So like, there's will be some flexibility about them. I just had to like do like a particular time for now, but like, that will probably change throughout the semester because there like, the need for office hours is like not constant. So like there will be times where maybe they will be more useful than others. Um, in terms of like what to mention about the, like the way the course is structured, like the most important things, well, you can find the like the well, I'll say that a bit in a moment. So like, during like lecture time, like when we meet, like, in terms of like things that will be graded only we will have like the exams which will happen during class time, so those are like the dates for the exams plus the final like that is like during the final week, so that's on a different moment. um so like our first exam is like roughly like in 3.5 weeks or like a month from today, so once we're getting closer to that, like I'll kind of like give you some like practice exams and other things. But so yeah, like during class, like the most important thing that will happen are the exams, and then during recitation. So the way where like the way recitation will happen most of the time. So for example, tomorrow would just be for you to do like some review problems because like there's nothing really that we would have covered like really. So if for tomorrow it's mostly about like like use up other problems from like definite integrals like that you saw in Calc 1, but they're kind of like important like very soon. So it will be more like of a review. But like in general, like the way like like um the recitation will work is that I'll give you some problems for you to work on, which are more like kind of like exam type problems. And then during like the last 20 minutes or so of recitation, there will be like a mini quiz. But I will kind of like give you the problems of the mini quiz ahead of time. So like kind of be very explicit, like like the quiz will be this and this these problems. Like, I'm okay, I may give you 3 or 5 problems and then the quiz is one of those 5, but nothing like too crazy. Like, it really will be more or less like what I create, like I'll send an announcement telling you like questions for the quiz, and then like the quiz is just like that. So in a sense, like it's more like you literally would know what the problems are like before like the quiz takes place. So like it's more like for you to kind of like have like an incentive to like review the material uh like on a regular basis, and then like this like before the quiz, like during the session when you have like these workshop problems, they will be graded more like based like on attendance and completion, or like accuracy per se. So it's like you can work in groups or you can work individually, whatever you prefer. But later like I'll post like the solutions to them. But the idea is, it's more for you to practice like more like realistic problems, like the type that you would see on the exam. So that is kind of like, in terms of like the like lectures and recitation, those are the two most important things. We also have like, like these like online assignments, which if you have taken Calc 1 at Rutgers, you know how Pearson works. But like at some point, like probably either this week or next, just try to like enroll on the Pearson assignments so that you can have access to the textbook and the online problems. And then I think I don't know if I wrote the weights here, but if you click on on the grading weights. Okay, yeah. Oh, okay. Here, like, is like the formula. It kind of goes into more detail, like, of how like the grade is computed for the course. Like, so those are kind of like preliminary letter grades, meaning like, if you get like a 75, you're guaranteed to get a B could be that by the end of the semester, like, the B starts at 74, 73, or like, like that can be adjusted, but it only gets adjusted downwards. So like, these guarantees the letter grades, but like depending on the circumstances, it could be that you end up needing a bit less than that. But at least that gives you kind of like an idea of like where you stand. And also like after each exam or something like that, I'll kind of tell you the scores were like this would have been kind of like the letter grades for the exam. If if we had like letter grades for specific exams, just to kind of like give you like a sense, like, where you stand on the course. And besides that, I did create like I don't know why is it not published. I don't know, like, I don't know. So this is like, okay, this is like for, like, that's kind of like the practice exams, which will be posted later. Like, sorry, like if you go to the assignments, um, yeah, I did create like a poll. I don't know why it's not visible. I don't know if anyone, I think you have had some of you, okay, so some of you already have answered. So like, I don't know why it says like it's not visible, but apparently you can see it. So it's just like, if you have the chance to complete it at some point, gives me like a better idea, like, of the course, of why you're taking the class. Yeah.
Unless we directly click the link to the assignment,
Uh-huh.
we can't see the assignment.
Oh, that's weird. So I'll try to see what's, well, thanks for letting me know. Yeah, like this is like the only class where this is happening, but like, I'll check what it is. But if so, in the meantime, yeah, try to click on the link to the assignment directly, and I'll try to fix that. In general, like, I do like to send like regular announcements. So after I have like we finish a class, I'll kind of tell you we covered this and this topics from the book. I'll be recording the classes. So I'll send you like the link to the video. If for whatever the reason you cannot come one day, or I don't know, or you want just to review the material, that's fine. So I'll send you a link to the video, and I also like will write on the iPad. So I'll kind of like send you like the notes. I mean, I will write in real time. I don't like kind of like using slides or anything like that, but at least I will share kind of like the notes of like the day. So that's kind of like how I'll usually run the class like on a regular day, except for like the exams. Are there any questions so far, Sophie? Uh, and like for now, there's not too much to worry like about. Like as the course progresses, I'll just let you know what you need to keep an eye on. So as I was saying, my plan for today was just to give you like a brief introduction to the course, and then kind of like start with like some of like the material, but like again, like probably not too much. So let me see if I can stop sharing. Yeah. Let's see if this works, because I haven't done this. This last time I did it was a while ago, so. Okay, so, in general, like the way calculus is set up to work, like broadly, it's like it has two main components, right? Like, so one piece of it, like important piece, is like derivatives. And that is like, in a sense, it's like 80% of Calc 1, right? Like you spend a lot of time like talking about derivatives in Calc 1. There's not much that we need about for with them for the moment, for the next few days. But like, so derivatives is where you spend a lot of time, which like one of the main applications, just like remind you of those, is that when you have like the graph of a function, right? Then the derivative is like the slope of the tangent line, right? So the slope was, which you could call m, is f prime of x, right? So again, like that is one of like the main purposes of like having the derivative around. I don't know if this is actually recording. I don't know why I cannot. Just sorry, give me a second. Just wanted to check that this is recording. Okay, yeah. So Oh yeah, I see it now. Okay, so just to get back, that's one of the main applications for the derivative. And then the other big topic in calculus is like the integrals, right? And that actually is going to be one of like the big things like that we will do in this course. So almost like 30-40% of the class is just like going like into more detail in how integration is supposed to work. So like this will be like key point of like this class. And like, again, like kind of like one of the original purposes for like doing integrals, which actually I'll kind of go back to in a bit, is like, to find areas, right? Like, so one of the selling points of like doing an integral is that, like, let me use a different color, is that if you have like the graph of a function, um, and then you have like an interval a b, then like the area between the graph and the x-axis like is being computed by the integral, right? So like the area in this case would be written something like this. And again, like I actually have to say a few more things about that later today. So like I won't spend too much time like on this particular point. But that is one of the main reasons why like you talk about integration. And of course, like there are other things, well, not that many, like that you did in Calc 1 with integrals, like finding average values and other small stuff. But like the point of Calc 2 is like kind of like go into more details into what are other things you can do with integrals besides like finding areas. Now, there is a third thing, like that's kind of very important in calculus, which is also something we will cover in this class, which is related to something that's called like a series, which you may have heard of or not, but let's put it as a like kind of like the a third piece of calculus. Okay. So a good way to like explain what a series is just to give you like an example. Like, and so like let me just do that. Okay, so here's an example of how a series works like. Um, okay, so let's say you have like the graph of a function and like a simple function, like which graph you probably remember, like the exponential function. Okay, so that is the graph of the exponential function, right? And it's kind of like nice because it's already like singling out this point. But a typical calculus problem would have been like find the tangent line to this point, right? Like to the points 0, 1. So let me put it like on the board. One the equation of this tangent line, right? So what is the equation of a line? Is y equals mx plus b. Okay, so it will pass like through 1, so like the intercept of the line would be 1, just because this is like the point 0, 1. So it would be y equals mx plus 1, right? And then how do you find m? And that's really where like the important thing from calculus kicks in, because m was like the derivative, right? So the derivative of the exponential, that's kind of like the fun thing of about the exponential is that it's its own derivative, right? Like that's like actually important to remember for this class. So that gives you like the derivative at any point, right? But we don't want the value at any point. We just want it at x equals 0 because that is where we're trying to find the tangent line, right? So like you said, like so more explicitly, like like the slope that you pair for this line is f prime of 0, which is e to the 0, right? So that would be 1. So the equation of the tangent line is actually y equals x plus 1, right? So let me draw that here. Actually, let me write it as 1 plus x. It's the same, but like it's convenient for what I'm going to do. Is that okay? So far, so good. Kind of like hopefully like a refresher. Okay, so why do you care about the tangent line, right? Like, and so the usual story about why the tangent line is important is that the idea is that if you have a graph, like definitely the exponential function is not a line, but if you have a graph and you start zooming in, right, at near a particular point, right, then the difference between the the graph of the function and the tangent line kind of like starts disappearing more and more, and that can be made more precise with the limit stuff. But like the way to think about of the tangent line is that it is like kind of like an approximation to what the graph of the function is, right? It's like the first approximation that you can try. Oops, let me zoom out again. But then and here's like a very natural question, and that's actually one of the things we will spend more time talking about in this class. You could say, okay, why do you want to stop? Like, so think of the tangent line as a way to approximate the function, right? Here at this point, but you could be like, okay, but there are tons of different functions, not just lines. So you could try to approximate the graph with something else that's not a line, right? So in terms of like complexity, like of like after a line, parabolas are kind of like the next next thing in terms of like complete, like big like difficulty. So you could try to be like, okay, maybe I could try to approximate the graph of the exponential function with a parabola. Okay, and in fact, it can be done. And we'll study later how do you find the parabola, but like at least I'll write like what the parabola is in this case. So it's 1 plus x. So essentially it starts like with like kind of like starts with the same formula as the line, but then because it's a parabola, you have to add something with x squared. Okay, so what you add up with x squared is, and again, like this is kind of like a bit magical in this moment. How you kind of like come up with this, but you add x squared over 2. Okay, so the difference between this is what you would call like sometimes a linear approximation, and this is like the quadratic approximation because it uses like a quadratic formula. Okay, is that it is the same as a linear step, but you add like a term that it depends on x squared. And so you can just compare and contrast and like notice that it looks better. Like, for example, so okay, there's a bunch of colors like appearing here, like, like this was the original function, right? The blue one is like the linear approximation, and the red one is like the quadratic approximation. So maybe to put like all of them at the same time, like kind of like near here, everything kind of like it's just very different to distinguish them, right? Which is which, like, because that's the point, like once you're close enough, like everything kind of like looks the same. But like, if you kind of move a little bit away, you can see that the red is kind of closer to the green for like a bigger interval, right? Like kind of like there's like a bigger gap between the blue and the green than the green and the red. So in a sense, that tells you that the quadratic approximation is better, right? And then, okay, well, you kind of see where I'm headed with this. You would say, okay, but why stop at something quadratic, right? Like, can be keep going, right? So after x, like after something with x squared, in terms of like complexity or like difficulty, like you would try something cubic, so something with x cubed. So the way that's supposed to work, and this is actually what's called like a Taylor approximation or a Taylor polynomial, but like it's like something that we'll talk about like later. You literally start with what you had before, so it kind of always refers to the previous step. That's kind of like a nice thing. So you would put 1 plus x squared over 2, okay? And then it's supposed to be cubic, so I have to add something with x cubed, right? And then and then you this like the question is like, is it x cubed or 3x cubed or minus x cubed? Like, you know, what number in front of x cubed? And again, like there's a way to determine that, which we'll talk about a bit later in the course. But in this case, like it ends up being x cubed over 6. Okay. So that gives you like the orange one. And again, it's kind of hard to tell, but like if you kind of notice, like the orange is closer to the green than the red was to the green, right? So it is a better approximation, right? And just to do one more step, you could say, okay, after y x cubed, what would follow? X to the 4, right? Which doesn't have like a particular number, quartic, I guess. So how does it work? You keep the previous stuff. You can imagine writing like a computer program, right? Like because it's kind of like the steps always refer to the previous step. Like, you know, you just add like an extra term. So like you can imagine programming this if you wanted to try, like once you had like the formula, there's a formula for it, of course, but so. And then the magical number that goes into here is 24. And that is purple, and that is kind of super hard to tell, but you know, like where is like now there's almost like the purple is completely on top of the green one. So I have to kind of like zoom a lot more to kind of like see the difference, right? But the idea, okay, and that kind of like goes to my point, which is maybe I should write this like on the iPad because like this is where I want to stop with this for the moment. Let me put it here. Okay, let me share again. Yeah, so just to summarize what I was saying, like the pictures won't, like I won't try to do the pictures because like here, you know, it's kind of hard to draw, but what I was saying with like this, with this thing is that you could have like something like f of x equals e to the x. And so the linear, I don't think the colors are the same, but the linear approximation in this case would be like 1 plus x, and then the quadratic one was 1 plus x squared over 2. And then the cubic one is 1 plus x squared over 2 plus x cubed over 6. And then let's just use a different color. What I would call the quartic, if you like, would be 1 plus x squared over 2 plus x3 over 6 plus x to the 4 over 24. Okay, and the point, like, so the idea is that there's, you know, kind of each of these is closer to the exponential, but they're never quite the same, like literally, right? Like there's always some gap between them. So if you wanted to kind of make this like that's kind of like the cool thing. If you wanted to make this identical to one of these formulas, you have to add infinitely many terms. So you have to add like x to the 5 and x to the 6 and x to the 7 and x to the 8 and x to the 10 trillion and x to 100 trillions, trillion, like what, you know, a gooplex or whatever like these numbers have. So like each approximation gets closer to e to the x, right? But you know, to have like an actual equality, to have like an equality, you need like infinitely many terms. Like you need infinitely many terms. And of course, like that is what we'll spend like later on time discussing. So I won't kind of like try to write like the formula in full detail. But like what I'm trying to say is that this goes like with dot, 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 dot. Like it goes forever. Like it literally never ends, like the formula. Um, so of course you have to have like a nice way to write that. If something goes forever, like probably like the infinity symbols like lurks in the picture. So like the fancy way to write this, like as a mathematician, is that you would write like something like this. So again, like don't worry about this for now because it's just kind of like something we'll spend more time later on. But this is just saying, okay, this weird symbol, I don't know if you have seen it before, but it's just like a way of saying, I'm going to add a bunch of stuff, right? I'm going to start with n equals 0, and I'm going to end at infinity, which means it's another way of saying I'm never going to end, right? So this would be x to the n factorial. And in fact, oops, this kind of like died. Let me open Notability again. Sorry about that. And then n factorial, like again, if you haven't seen it before, it just means like n times n minus 1 times n minus 2 times 2 times 1. So for example, 3 factorial is 3 times 2 times 1, which is 6. And 4 factorial is like 4 times 3 times 2 times 1, which is 24. And that is how these numbers, 6, 24, were showing up when I was writing them before. Here. So this was like 3 factorial, and this was 4 factorial, and the next one would be 5 factorial, which would be 120. So the next one would be x to the 5 over 120. And then what is after 120 times 6, like what, 720 or something like that? And then it would x, like, x to the 6 over 720 or whatever it is. So it goes, but the important thing, like, to understand, like, here is that this goes like for eternity. Like, it never ends. Like, so, like, to make it precise, we need to throw in some limits and a bunch of other stuff. Which again, there are details that we will discuss later on. But that is kind of like, in a sense, like the third big piece of calculus, which may kind of like be not super clear. Like, when you take calculus at the beginning, that is something also that we will do. And that is really like the way in which you should really think of this as like an approximation, because obviously, like, say, if you were to compute this, put on a computer, like you could never put on a computer something that goes up to infinity. But like the error is, sufficiently small for whatever practical purposes after you throw in a couple of terms, right? So in practical, in fact, like the way most of the things are actually computed in practice is like you use like an approximation of this sort, like, in terms of polynomials. And that gives you like, up to the desired accuracy, like the answer. But so like this is like a very important concept because like it is like a way to like describe functions. Like the exponential is completely, it's like a completely different thing from like a polynomial, and yet like you can use polynomials to study them. That's kind of like the cool thing. In fact, you can kind of like do some like, maybe I'll wrap this like as an introduction before like getting into more like details of what I want to actually mention. But like this is kind of like fun to kind of like always like do. So I like this. In fact, like, yeah, so like the idea of like, like the idea of like something like this is like you can approximate like a graph with polynomials. There are other ways to approximate functions, like, you can use sines and cosines and things like that. So like, we will talk about curves, late, kind of between before series and after integrals, kind of like squeezed in between. So you can have like a curve, like a Santa Claus curve, and you have to describe it using a function, and like it's like a massive function that you would use here, like in this case. So, but like, and again, we'll talk about that later, how you will do it. Like, so this is like an insane formula. The important thing is that this is just a bunch of signs. Sign, 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 sign. You don't see anything that's not a sign. The only thing that you're changing is what physics is called like the frequency or the period, But that kind of like the idea there is like in the same way in which you can approximate a function using like x squared, x cubed, x to the 4, x to the 5, etc. You can approximate a function using sines or cosines, like actually it doesn't matter too much. And that is called like a Fourier series. So like series are everywhere, like like kind of like ways to approximate, and that's kind of like probably like the nicest topic of the course, in my opinion, because like that just like opens up like a lot of like things you can do with calculus. But like the important thing is like it kind of like you should think about them as like it's like an attempt to add infinitely many things, and when you try to add infinitely many things, you have to be careful. And like we will go over like what can go wrong when you try those things, but like many things work well. And by the way, like if you got like there are tons of like different curves like you can try, you know. You can put like your Biden curve, but like it's kind of funny. It's like so there's like a curve for like every politician in the United States, I think. So you can just try. Okay, like this one is taking time to compute, but like it will it will give you a massive formula in terms of sines and cosines. Like okay, for some reason it's being kept like a state secret, but like it really like what. Okay, this is another one, like kind of fun, like like, and again, like the important thing is that there are a bunch of signs that appear, and cosines. I mean, cosines could appear as well, but like a sine is really like a cosine, like just shifted. So that's why it doesn't matter too much. Okay, so that's just kind of to give you like a sense of some of the things that we will do in this class. So again, to repeat, like in derivatives, not so much. You already kind of like did the majority of the stuff related to derivatives in Calc 1. Integration, that's more important in this class. So yeah, we will go into more detail into integration, and also series, which is kind of like the other big topic of Calc 2. Okay. Any questions about this so far, so good? Okay, so now I will kind of like just start with some basics about integration, because like that is like the first topic. So we finished at 7 today, right? Like, okay, perfect. Just keeping in mind. So the first topic will be integrals. So as like I kind of mentioned a bit earlier, like the original, like the initial way to think about integrals, which is convenient at first, is that if you have the graph of a function, let's put something like this. If you have the graph of a function and you choose like an interval, then the integral, right? When you wrote like in Calc 1, like the integral of f of x dx from a to b, what that's supposed to give you is like the area between the graph and the x-axis. But the way it's set up to work is that actually it's more like a net area, because when the graph, is above the axis, that counts as positive, and when the graph is below the axis, that counts as negative. That is like ends up being like actually like a convenient thing to do. So it's like, when you think about this like integral for the first time, like you can really think more accurately of it like being like some sort of like net area. So I'll just use different colors to like indicate that. So this is counted as positive area, right? And this one is counted as negative area. Right? And of course, you could alternate positive, negative, depending on what the graph is like. But the important thing is like, it is like a net area in general. Okay, so that is what it gives you. The other thing that's important to remember about it is that actually how is it found? Okay, so like that is where like the fundamental theorem of calculus like really makes appearance, because the cool thing about like the fundamental theorem is that it says, okay, if you want to find the value for this, you find like an antiderivative, right? So you find a function whose derivative is f of x, right? So what was like, it's just like as a refresher. So like the idea is like you find that is a function. Sometimes like they just like that function is referred to as like uppercase f. So a function whose derivative is f of x. And then what the fundamental theorem of calculus says, like let me put it like in a different color, is that it is, you just like evaluate that antiderivative at the endpoints and subtract the answer, right? Um, so just to do like a very specific example of how that worked, like let's say I wanted to do like, I don't know, like the integral from -1 to 2 of x cubed dx, right? So let me see, put it here. So what does that mean? In practice, like how did that work? What that meant is like, okay, you're trying to find a function, right, whose derivative was x cubed, right? Like you're like that's how you're supposed to evaluate this integral. So you're trying to find a function with derivative equal to x cubed, and then you have to kind of like think about the derivative rules backwards, right? So you remember, okay, something like x to the 4, right? Like x to the 4. Is 4x cubed, right? Like the 4 comes down, and then you lower the exponent by 1. So that's how the rule works. And so you say, okay, so this is almost, x cubed, except for this annoying factor of 4. But then you divide both sides of the equation by 4. And that kind of works because like the constants can be put in or out of like an integral, sorry, of a derivative. Right, which is just, which is like a more like specific case of like the formula, that like x to the n over, So like what that means is that like an antiderivative, because there were other options, like they all differ by a constant. An antiderivative for this is just x to the 4 over 4, right? Evaluated at x equals 2 and at x equals -1, right? So that what does that mean? It means you're doing 2 to the 4 over 4 minus 1 to the 4 over 4, right? So that's how the formula will work in this case. And so what is 2 to the 4? That's 16, right? So 16 over 4 is 4. And then, -1 to the 4, that's 1. So like -1/4. And this is like what? 16 minus 1 over 4, which is 15 over 4. So hopefully I didn't do like any silly mistakes. But that is like in general, how we do most of these integrals. Of course, like the USUP was like an important tool for that. And that's one of like the things like the review, the recitation tomorrow will be more like USUP type problems, because those are more tricky than just like a direct formula, like application of this formula. Okay, but my point, like the reason why, I'm going back to this is just because in a sense, like, if you were talking about, oh, how do you find a definite integral? You know, like the rule from Calc 1 is kind of pretty direct. Like, you know, you find an antiderivative and then you just like evaluate the antiderivative of the endpoints and subtract. Okay. So far so good. Now, so there are two things to say about this. Like in some cases, like maybe finding an antiderivative is very, very hard. Or more generally, you can just you could just be interested in like that like way in which the derivative was actually defined, because this is not how the derivative is defined. It just happens to be like a very nice like miracle that it works this way. But like the actual definition of like the of the integral. I don't know why I say said derivative. This is not the way that the integral was defined. It just happens to be the case that it works this way. The way that integral is actually defined is like with Riemann sums, and that's actually like a useful thing to remember. So like, let me write that down. The actual definition of the integral involves what is called like a Riemann sum. Okay, so what was this? Because this is actually important for like something I'll do in a moment. I think I should have time to do it today. So what was the idea behind a Riemann sum? Let me maybe show you first like on GeoGebra, and then I'll kind of like do like a sketch on the iPad. But okay, so the idea behind a Riemann sum, where do I have it here? Oh, here it is. Okay. So yes, this is okay. So this was like the idea behind the Riemann sum. So you have a function. In this case, like the function is sine times square root of x. That's the graph of that function. Doesn't matter too much. And you have like an interval. So in this case, like the interval goes from 1 to 9, which is here. Okay. And so the idea is like to approximate the area, right? We wanted the area. You know, we cannot compute like this area directly. So like the idea of like the Riemann sum is kind of like to chop off like the graph into rectangles, more or less. And those rectangles kind of like serve as approximations to the actual area that you wanted. So let's see, use like the right point approach. So first, like the first thing you could do is like, okay, I'm just going to approximate the area with a single rectangle, which is like a terrible approximation, right? Like this doesn't give you really anything too useful. But the idea is like as you chop it off and make them thinner, so that like the endpoint, like the idea is like the endpoint of like the rectangle ends on the graph. You know, like actually, let me see if I can make this a little bit bigger. You know, as you increase the number of rectangles, oops. So now I have 2 rectangles, and then I have 3 rectangles, and 4 and 5 and 6 and 7 and 8 and 10. Now I have 10 rectangles to approximate the area, and this does look a lot closer to like the actual area, you know, between the graph and the x-axis. Again, if you kind of just keep in mind that would be counted as negative area, but like that's fine. And then like, you know, when the approximate, like if you continue the approximation, make the rectangles thinner. Like already like at 68 like subdivisions, like it's more or less identical, right? And of course, like that's where the limit kicks in, because like to make this like completely correct, you take the limit as n goes to infinity, which in practice you never computed like the integral that way, but like, you know, theoretically that's what's supposed to happen. So, you know, you kind of go forever and forever and forever and forever and forever. So like 200 is too little, right? Like you have to go to 2 trillion, then 20 trillion, and 20 trillion to the trillions, like, you know, that goes forever. But like, of course, in practice, like for many functions, if you were to put this like on a computer, like maybe already like in the third year, subdivision, then you're good to go. Like in the sense, like it's within error, like pretty good. But like the idea is, like the integral really is some sort of infinite sum. So it's actually secretly related to a theory when we were talking about theory earlier. But the idea is like an integral, the most useful way to think of an integral is actually as a device to compute like sums, like in a way, because this is like adding up a bunch of areas, or like areas of rectangles. So let me write that down. And that is like like that is the best way to like understand what like an integral like is. So and then I'll just do like an example and then finish for today, to show you how you can think about this stuff. So like just summarize like the idea. I was saying that you kind of break the graph or subdivide the graph, approximate the graph with all these like tiny rectangles, right? Okay. So like this is like an approximation. And then this integral is really like kind of like a sum, right? Sum in quotes because it really kind of goes forever, right? That's where the limit is supposed to work. But it's kind of like a sum of what is like the area of one of these rectangles. Like, so the idea is like if you look at one of these rectangles, let me just put this in color, what is the height of this rectangle? The height is f of x because like kind of like that rectangle terminates on the graph. So the height of the rectangle is f of x. And the width, right, is what you would usually call dx or delta x. Like it depends on, I'll just call it dx so that it looks like exactly the same as what you have here. Right. So it's like an integral is kind of like a way to add up f times a small width. Okay. So the idea is like in general, like the way to think about like an integral is that you can think of an integral as a device to compute some like really, really small sums, like, or like a sum of many terms. And that is not necessarily area. And in fact, I'm about to give you like an example of volume of how you can use this. So the idea is to think of like an integral, think of an integral as a way to add like terms of the form f of x times dx. But the important thing is like this is doesn't need to be like area. So it doesn't need to give area. Doesn't. Which is what I'm about to show you in a moment. I'm just going to give you some moment to copy this. Okay, so making sense. Okay, so let me give you like an idea, like an application of this idea for something that like we are familiarized with, like a sphere. So let me show you how this works with a sphere. And then next time I'll kind of give you like a more like precise formula that works not just for a sphere, but a bunch of other stuff. But at least I wanted to show you with an example that will be the last thing I do today, like how this would work with like stuff like that is not like a sphere, like which is not like just like an area. Finding the volume of a sphere. So like maybe to kind of like summarize what's going on, I'll put it on the board. Basically, another way to say of like the thing that I was mentioning is that when you have a graph, like the integral, what it does is break the graph into, into rectangles. Okay, so this breaks it into rectangles. But now, let's say I give you something like a sphere, which is something like in 3 dimensions, like, so it's not something I can draw on the XY plane. So let's say like I have a sphere. And like, so it could be like a ball, like an apple, like something round. So I ask you, okay, what's the volume of the sphere, right? So, if I wanted to try to find the volume of the sphere, one way you could actually do, I don't know if you would make a lot of sense. Hopefully my picture doesn't even do bad. You could try to break like the sphere into boxes, if that makes sense, kind of like towers, right? Like vertical towers. And in fact, that's what we're doing out three. So if you take out three, this is how you can find the volume of a sphere. This is not what I'm about to do now, because like a sphere, like, like boxes are kind of like not the most obvious thing with a sphere. Like a sphere kind of like works better with circles and discs, right? So like the way I want to break like the sphere, and I'll show you like that on animation like in a moment. But imagine that I have like a knife. I have a sphere, like I cut it, right? So how does the cut look? It looks like this. Then I take my knife, I cut it somewhere else. And now it looks like this. What is this thing? That is a disc, right? What is this thing? That is a disc, right? Let's go do another cut. That is another disc, right? So like there are like the point is that there are different ways to cut a thing, that makes sense. So for a sphere, it kind of makes sense to cut it using discs because I kind of like like these spheres are kind of like all like relatives. So just to show you that on like on GeoGebra before like giving you like the formula. Uh, yeah, like somehow it disappeared here. Okay, so where is this? Aha, here you are. So let's see. So I have like a sphere here. In this animation, it's kind of like a radius 5. That doesn't matter too much. But the idea is that you kind of think of the volume as being made up of like discs. I don't know if you can see the disc here, just with some thickness, like so it's like kind of like a thickened disc. So like in this picture, if I wanted to draw that, Um, it will look more like that, if that makes sense. So it's kind of like a thickened disc, and then the idea, of course, like depending on how, like the thicker the disc, there's like it's kind of like more like it works less well, like it doesn't work as good. You kind of want to make it very super thin. And then then you make the cut at different locations, right? And then you get different discs. But what I'm trying to say is that kind of like the way to think of the volume of a sphere is kind of like a sum of the volumes of all these like thickened discs. So like if you kind of chop it off, like chop the sphere into discs and then add them all together, that is more or less like an approximation for what the volume of the sphere should be. Is that making sense? Kind of like reasonable. Let me do like a picture on the tablet to kind of like illustrate what the point is. And you'll see how this is related to the integral. And that will be the last thing I do for today. Um, okay. Okay. So what I'm saying is that if you have a sphere, you can draw these like thickened discs. Okay. And so what I'm saying is that the volume of the sphere should be the sum of the volumes of these thickened discs. Okay. And so it all boils down to how do you find the volume of like one of those disks? Okay. So let's try to work it out. And that's kind of like the last thing I'll do today. And for that, you do have to kind of be a bit like strategic of how you set up things. And that's kind of what we will learn more about next time. So just think of this kind of like as an opening for like the stuff we'll do next time. But think of like the x-axis as passing through like the center of the sphere. So here's like the x-axis. Let's say that the origin of the sphere is like like the center of the sphere coincides with the origin. So here's 0, and here's r, and here's negative r. If you think of the sphere as having radius r, so the sphere has radius r. Okay. So if you have a disk, which I'll try to draw a bit more like thin, like I'll just try to draw the disk itself. Um, okay. Uh, if you have a disk, what is the formula for the area of a disk? Is pi r squared, or like the area of a circle, right? So if you call like, but don't get confused because they're kind of like this is kind of like a different r. So like this is refers to like the radius of this particular circle. So let's think of this circle as having certain radius. Okay. It looks better on the PDF, I promise. Like once I share it with you. So like the area of the disk is pi r squared. Okay. Like this r, right? Like pi r squared. But then how do you find this r? Because like it's not very convenient to leave the formula this way because you don't have r. But like the idea is that secretly there's like a right triangle here. I don't know if you can see it, but I'll make it more clear in a moment. So if like if this disk is kind of like at a distance x from the origin, there's like a right triangle where one side is like the radius of the disk, the other side is the radius of the sphere. Because remember, like the point of a sphere, the point of a sphere is that all the points on the sphere are at the same distance from the center. So this point is like a radius r from the center of the sphere. So like this, that's why the hypotenuse is like r, the radius of the sphere. This is like the radius of the disk. This is x. And so I don't know if you remember Pythagoras theorem. What does Pythagoras theorem say? It says that the hypotenuse squared, right, is like the sum of the squares of the other two sides. Is that okay? Is that rings a bell? And then you can solve for little r here. And so that gives you that the area of the disk is pi times r squared minus x squared. Okay. Why is that useful? Because then if you have like, if you take this disk and just move it a tiny amount delta dx, if you move it amount dx, it becomes thickened. So when you have like kind of like draw the sphere again to not make it like super like you know. If you have like now the thickened version of the disk, right? So like imagine that you thickened up the disk by some amount that you call dx. Okay. So the volume of the thickened disk of the thick disk, it should be the area. You just took the area and move it by an amount dx. So it should be like the area of the disk times the thickening times dx. Okay. And that gives you pi times r squared minus x squared times dx. Okay. Huh. But that is kind of like the sort of thing that appears under an integral, because on an integral, you have like something times the x, right? Like that's kind of like what integrals are, something times the x. So maybe if you integrate this from negative r to r, because those are the x values, right? Like just remember like that these are the x values. So here's where it was 0, here's negative r, here's the r. So in fact, what ends up happening, and again, I'll write like the general formula next time. I just want to wrap this up. But if you integrate this with respect to x from negative r to r, that will give you the volume of the sphere. So like the volume of the sphere, and that's actually called the disk method. So I'll kind of like write the formula more precisely next time. So volume of the sphere is going to be the integral from negative r to r of, let's put this pi r squared minus x squared dx. No, let me just help you out, like how you would do this integral. Like, you can take out the pi because like that's a constant. And then like, you can integrate each term separately. Right? So like, take out the constant, then break it into two integrals and subtract them. this is just like a constant, right? Like, so you could have taken this out as well, but like, so basically it gives you pi times r squared times x minus, and then what is the integral of x squared? It's x cubed over 3, right? And you evaluate that at the endpoints, right? So you're supposed to evaluate that at x equals r, at x equals negative r. So that gives you what? That almost done. So that gives you put x equals r here, so it gives you r squared times r minus r cubed over 3, and then put and then you subtract the answer at negative r. I mean, there are other things you could have used, because like this function was like what even, so like there's some symmetries or other things you could have done, but so that gives you r cubed minus r cubed over 3. That's 2r cubed over 3. And then this gives you minus r cubed plus r cubed over 3. So that's minus 2 r cubed over 3. So minus minus becomes a plus. They're the same denominator, so you just add the numerator, so you get 4r cubed over 3. And that is 4 pi over 3 times r cubed. And if you have ever seen the formula for the volume of a sphere, you will know that it is 4/3 of pi r cubed. Okay, so that is like a cute application, because it kind of like shows you, oh, actually you can use like an integral to find volume, not just area. You just have to understand what you're adding, right? So here we were adding secant this, and like I'll mention it next time, but like that is what the way of, like one way of finding volumes for certain regions is like by this method. Okay, so like we'll start that on Monday. Again, for tomorrow's workshop, presentation, it just will be like some review problems about like definite integrals, like U sub and things like that. But let's finish here, and like I'll send you the recorded video later in the evening. So let me stop here.